Okay, so today we're going to be talking about arithmetic sequences, and these are the simplest types of sequences there are. An arithmetic sequence is just a sequence of numbers where the next term is given by adding a constant. So we're adding a single number every single time. So in this sequence right here, this example, you can see that between terms we are adding 5. And that is the pattern. So we're adding 5 between every pair of successive terms. And this goes on forever. So plus 5, plus 5, plus 5. And we can express this very nicely using a recurrence relationship, for example. So in this case, we have un plus 1. This is the n plus 1th term. This is equal to un, the nth term, plus the constant. In this case, it's just 5. And then we also need to know the starting point, the first term, which is 2. So we start off at 2, then add 5 to get the next term, and then keep adding 5s to get to the successive terms. Okay, so now I want to take a step further, and we're going to generalize this process. So if we have a general arithmetic sequence, this is going to look like a plus d, a plus 2d, a plus 3d, etc., etc. So we start off with our constants. This can be a, let's call it a. So this is the first term. In this example up here, this is equal to 2. And then to get to the next terms, we're adding on d, and this is the difference between terms. So we're adding d between every single successive term, and that's the pattern for this arithmetic sequence. So again, we can express this as a recurrence relationship, and it's going to be very similar. We just replace the numbers by these constants. So in general, it's going to be un plus 1 is equal to un plus the difference, so d, and up here we had 5. And then we also need the first term, and this is just a. So this is a general recursive formula for an arithmetic sequence. And now we can also try and find the explicit formula. So this recursive formula works by feeding in a term and then getting the next term. But we want to find an explicit formula that, given the term number, given n, it will give us straight away what that term is. So I'm just going to go ahead and label these terms here by their term number above. So this is the first term, this is the second term, this is the third term, this is the fourth term, and this is going to carry on. And now you can see the pattern that in each term we've got an a, and that doesn't change. But if we look at the pattern between the constant in front of the d and the term number, you can always see that this, if we imagine this being a 1 here, then we can see that the term number is always 1 more than how many lots of d we're adding. So we can deduce that the explicit formula is going to be un, this is the nth term, this is going to be a, because every term has an a term in it, and we're also going to have n minus 1 d. And this is for n is greater than or equal to 1. And we don't need a starting term here in this case, because we can just feed in n is equal to 1, and this will give us the initial starting point. And we can check this is correct by, if we put n is equal to 1 in here, n minus 1 goes to 0, so we have 0 times d, and that's just a. So this does give us u1 is equal to a. And then if we were to increase the number of n, then we get, so if u2 is going to be a plus 2 minus 1, which is just 1, plus d, so a plus d, and this is going to generate the whole sequence. So this is an equivalent expression to the recurrence relationship. So we can use this idea and go back up to our example up here. Let's try and find the explicit formula for this sequence. And it's just going to be using this formula, and we're going to input these constants. So the explicit formula in this case is going to be un is equal to a, which is the starting position, so that's 2. And then we have plus n minus 1, which doesn't change, that's just the variables. So plus n minus 1 and multiplied by the difference, d. And in our case, the difference is just 5. So we multiply by 5 here. And this is still for n is greater than or equal to 1. So hopefully you should be able to identify what an arithmetic sequence is. We're just adding a constant number between terms, and realize that we can express this using a recurrence relationship and an explicit formula. And down here we've written the general cases for the recurrence relationship and the explicit formula.